Okay, so previously we had discussed methods that we could use to help us find the absolute extrema of a function on a closed interval. And we said that an absolute extrema can only occur in one of two places. It either has to occur at a critical number or it has to occur at one of the endpoints. Today, what we're going to look at is what we can tell about where a function is increasing or decreasing based on its derivative, and how we can locate relative extrema for a function. So to start off with, we just want to kind of clarify what we mean by increasing and decreasing. So visually, we kind of already have an idea of what increasing and decreasing means for a graph. We know that a function f is increasing on an interval if for any two numbers from x1 to x2, the interval, if x1 is less than x2, then the function value at x1 is also going to be less than the function value of x2. In other words, the function is increasing if as x gets larger, our function values get larger as well. And then the opposite of that would be decreasing. So we say that a function f is decreasing on an interval if for any two numbers x1 and x2 in the interval, if x1 is less than x2, then f of x1 is greater than f of x2. In other words, we know that the function is decreasing if as our x values get larger, our function values, our y values are actually getting smaller. And so previously we discussed this idea of using the derivative to determine where something is increasing or decreasing, because we know that the derivative is measuring the rate of change. And we said that if the rate of change is positive, then that means that the function must be getting larger. And if the rate of change is negative, then the function must be getting smaller. So to test for intervals where the function is increasing or decreasing, we know that if the derivative of f is positive, greater than 0, for all x values in some interval, then f would be increasing on that interval. If the derivative of f is less than 0, is negative for all x values in some interval, then that means that the function must be decreasing on that interval. We've also kind of talked about this idea before. We know that if the derivative is equal to 0, then that means that there's no change, which would mean that if the derivative is equal to 0 on an interval, then the function must be constant because there is no change on that interval. So if we put those things together, we can come up with a method for locating where we have our relative maximums and minimums, our high points and our low points on the graph of a function. So let's say that c is a critical number. And previously we said that a critical number is a place where the function is either, or the derivative of the function is either equal to 0 or possibly does not exist. So if c is a critical number on a function, f, and that function is continuous on an interval that contains c, then if f is differentiable on the interval, except possibly at c itself, because we could have like a sharp point that is causing it to not be differentiable at that instant, then the point cf of c can be classified as one of the following. If at that critical number c, the first derivative changes from being positive to negative, then we can say that there is a relative maximum at that point. In other words, if the derivative changes from being positive, then the function was increasing, to negative, then the function is decreasing, then that must mean we have some high point there on the graph. Therefore, we have a relative maximum. And likewise, if the derivative of f changes from being negative to positive at that critical number c, then at that point we must have a relative minimum. Because if our derivative changed from being negative, then our function was decreasing, to positive, then after our function was increasing, then that means we must have had some kind of low point happening at that graph, and thus a relative minimum. So let's take a look at how we can apply this to a specific function. We're going to find the critical numbers of f, the intervals where f is increasing and decreasing, and then we're going to use that to identify all points that are relative extrema. So in order to find the critical numbers, the first thing that we're going to need to do is to figure out what the derivative is. And we have x to the fourth plus 1 divided by x squared. Now, we could approach this using quotient rule, but a little bit of manipulating with our function before we get started will make it easier to find the derivative, because this is x to the fourth divided by x squared plus 1 over x squared. We could rewrite this as x squared plus x to the power of negative 2, which makes it a lot easier in our next step to find the derivative. So if this is true, then our derivative would be 2x minus 2x to the negative 3, or 2x minus 2 over x cubed. Now we know we're going to have critical numbers where this is either equal to 0 or where the derivative doesn't exist. To help us solve this, I'm going to go ahead and get a common denominator here. So 2x would be the same as 2x to the 4th over x cubed, just multiplying the numerator and denominator both by x cubed, minus 2 over x cubed gives us 2x to the 4th minus 2 divided by x cubed. So now that we have our derivative, we can go ahead and find our critical numbers. We know that our critical numbers are going to be where this derivative is either equal to 0 or where this derivative does not exist. And I think that the part where the derivative doesn't exist is pretty easy to see. This would have an issue if the denominator is equal to 0. Then obviously the derivative would be undefined. And in order for the denominator to be equal to 0, then that would mean that x has to be equal to 0. So one of our critical numbers occurs where x is equal to 0. In order to be equal to 0, the only way that a fraction could be equal to 0 is if its numerator is actually equal to 0. So to find where the derivative is equal to 0, we're looking for where 2x to the 4th minus 2, the numerator, is equal to 0. We could factor this. So I'm going to factor out the 2, and we have x to the 4th minus 1. We can factor this further because that's a difference of 2 squares. So that would happen where we have x squared plus 1 times x squared minus 1 equals 0. And we could even factor this piece a little bit further because this gives us a difference of 2 squares again. So fully factored, we have 2 times x squared plus 1 times x plus 1 times x minus 1. And so in order for that derivative to be equal to 0, any of these factors would have to be equal to 0. Obviously, 2 is not going to be equal to 0. If we take our first factor, x squared plus 1, and set it equal to 0, then we have x squared equals negative 1. And of course, if we try to take the square root, we're not going to get real numbers. So there's no value that's going to make this factor equal to 0. This one, however, if I take x plus 1, set it equal to 0, then that means I have a value of 0 when x is negative 1. So that's another critical number. And if I take my last factor, x minus 1, and set it equal to 0, then I would also have a value of 0 if x is equal to positive 1. So no real numbers here. But overall, we have 3 critical numbers. 1 where our derivative would not exist at 0, and 2 where our derivative is equal to 0. 1 at x equals negative 1, and 1 at x equals positive 1. So that takes care of our critical numbers. Now we can use those critical numbers to determine where our function is increasing and where it's decreasing. In order to change from increasing to decreasing or decreasing to increasing, that means that our derivative would have to change signs, either from positive to negative or negative to positive. And the only way to change sign from negative to positive or positive to negative would be to cross through 0. So to cross through 0, we either have to be equal to 0, those 2 critical numbers, or sometimes we could jump across 0 because we have something that is undefined, and that's where our other critical number is. So not only are our critical numbers our possible locations of relative minimums or maximums, they're also the possible places where our function might change from increasing to decreasing or from decreasing to increasing. So I think that the easiest way to determine where we have increasing and decreasing is to kind of think of like a number line. And what I'm going to do is I'm going to take all of my critical numbers, I'm going to put them on the number line. So I've got -1, I have 0, and then I have +1. And what I'm going to do is I'm going to take a point in each of these intervals, and I want to determine whether or not the first derivative, f prime, is going to be positive or negative. If I know where the derivative is positive and negative, that's going to tell me where my function f is increasing and where it's decreasing. So if I look at my derivative, if I plug in a number that's less than -1, well, if I plug a negative number into the numerator, when I raise it to the power of 4, it's going to become positive. And specifically, maybe we'll take a specific example like -2. If I put -2 in, then I'm going to have 2 times 2 to the 4th, whatever that is going to be bigger than 2. So the numerator would be positive. But then the denominator, when I cube it, -2 cubed is going to give me a negative number. So I don't necessarily have to know the exact value of the derivative. Really, all I need to know is whether or not the derivative is positive or negative. And in this case, I know that at -2, my numerator will be positive, my denominator will be negative, and a positive divided by a negative is going to give me a negative value. And then I can continue on in that pattern. So if I plug in a value between 0 and -1, maybe something like -1/2. If I take -1/2 and raise it to the power of 4 and then multiply it by 2, I'm actually going to get something that's smaller than 1. And if you're having a hard time imagining that, think about it like this. That would be 2 divided by 2 to the 4th, which would be 1 over 2 to the 3rd. So that's going to be something that is less than 1. So I've got something smaller than 1 minus 2, which means the numerator is going to be negative. Then my denominator, again, if I plug in a negative number here and cube it, I'm going to get a negative. So my numerator is negative, my denominator is negative, and a negative divided by a negative would give me a positive. All right, now I'm going to plug in something between 0 and 1. We'll go with +1/2 this time. Following along the same train of thought, I'm going to have 2 times 1 over 2 to the 4th, which would give me 1 over 2 to the 3rd, which is smaller than 1. And if I take a number that's smaller than 1 and subtract 2, I'm going to get a negative. So at 1/2, I know my numerator is negative, but this time my denominator, I'm cubing a positive number. And when I cube a positive number, I'm going to get a positive. So I have a negative number divided by a positive number, which is negative. And then finally, my last point, I need to check something that is larger than 1. So we'll go with maybe 2 this time. If I put in 2, I have 2 to the 4th times 2 gives me 2 to the 5th. Minus 2 is going to be a positive number. Over 2 cubed is going to be a positive number. And a positive divided by a positive gives me a positive number. So what does this tell me about my function? Well, everything that is less than -1 is going to have a derivative that is negative, which means that in this region, my function would be decreasing. Then everything between -1 and 0, I'm going to have a positive derivative. So that means that in this region, my function must be increasing. Then again, from 0 to 1, I have a negative derivative telling me my function must be decreasing. And then finally, for everything greater than 1, I'm going to get a positive derivative, meaning that my function must be increasing. So my function is decreasing, increasing, decreasing, increasing. So for the intervals where we are increasing, we know that f is increasing. For the values between -1 and 0, so from -1 to 0, and also for all of the x values greater than 1. We want to make sure that we justify our answer, and we need to do so in terms of the first derivative. So how do we know that f is increasing on those intervals? Well, because on those intervals, our derivative, f prime, is greater than 0. You could also just say that f prime is positive, but this part is important. You must justify your answer. And unfortunately, this little number line that we created here is a great way of organizing our thoughts, but it's not really considered justification. So you actually have to write out an explanation. So you could either say because f prime is greater than 0 or because f prime is positive. They also want us to find where it's decreasing. We know that f is decreasing everywhere that x is less than -1. So for all x values less than -1. And we also know that it's decreasing between 0 and 1. So all of the x values between 0 and 1. And again, we know that this time because the derivative of f is negative or less than 0. And now finally, we need to determine our points of relative extrema. So we know that at -1, the derivative changed from negative to positive. According to our first derivative test, that means that this point at -1 is a relative minimum, provided that that's a point on our graph. So as long as our function is defined at -1, we should be okay. Well, let's see what happens. At -1, I have -1 to the 4th is 1, plus 1, divided by -1 squared is 1. So we would have 2 divided by 1 is 2. Then, at 0, our derivative changes from being positive to negative. So according to the first derivative test, we must have a relative maximum there so long as this point is a point on our graph. So at x equals 0, we would have a denominator that's equal to 0. So in this case, this could have been a relative max, but since that's not a defined point on our original function, without it being a point, obviously it can't be a high point. So we had a possible relative max, but that point is not actually defined on our graph. Had it been, then we would definitely have a relative max at that point. And finally, if we look at x equals +1. At this point, our derivative again changes from negative to positive. So according to the first derivative test, we have a possible relative minimum at this point, so long as that point is defined. And if we evaluate this function at 1, then we would have 1 to the 4th is 1, plus 1, divided by 1 squared is 1. So again, we get a value of 2. So we do not have any relative maximum points because this one wasn't actually a defined point, but we have 2 relative minimums on this graph. So we can conclude that f has relative maximums or max points at the point -1, 2 and at +1, 2. And we know that, again, we need to give some justification. We know that those are relative, oh, I'm sorry, that's not a relative max, is it? That's a relative minimum. Sorry, those are relative minimums. And we know that they're relative minimums at that point because our derivative, let's try that again, because the derivative changed from positive to negative. And we need to make sure that we justify that. So we know that because the first derivative test tells us that if the derivative changes from positive to negative, we must have relative minimums at that point. So those are our relative minimum values. Our next example wants us to find the open intervals on which f of x is increasing and decreasing. So this one is a little bit less work. You're just finding the intervals where f is increasing or decreasing. I'd like for you guys to try this problem, and then when you're ready to check your work, go ahead and start part 2.